Okay, so when you talk about feature extraction, so there's basically like several features that we can look at, right? When you look at an image, there are certain features that you can look at. Uh, so uh, so if you look at the image, basically color could be taken as a feature. Like there's different types of features. But in our case, we'll not be looking at those basic features, but we'll be looking at mainly three types of features. That's edges, corners, and blobs. In this case, of course, our primary focus will be how edges and corners, these two features are identified rather than blobs. So blobs, we'll see what blobs are like in a very high level, but our focus mostly will be on uh, corners and edges, right? So I think most of you all already know how to find corners, how these corners are found. So you all have this basic idea, right? So we'll talk about this. So when you talk about edges, you can see that if you look at this image, right? This is a captured image. You can see uh, there are several types of edges, right? There's an edge here, separating the image from the background. And in here also, you can see that there's a small edge. Where you can sort of differentiate. There's a person here. And between the two surfaces, also there's an edge. So also you can understand that there are edges like separating. So you can see that uh, you can see the entire idea of why we are very much concerned about these edges is that edges actually help us understand and like differentiate certain objects from a picture, right? That's why we are very much concerned about edges rather than just looking at. I mean, there should be a reason why we are looking at edges, right? I mean, when there are so many other features to look at, right? So you can see if you look at this image, there are certain other features that you can look at and that you can like try to detect, right? But why we are very much concerned about edges is that it's very much useful for us to differentiate certain uh, images. So, or rather, we can say it can like help us identify sudden changes or discontinuities of an image, right? So, you look at the definition of edges. So, basically, the idea is or the goal is to identify sudden changes or discontinuities of an image. So, if you look at this person's face, right? So, you can see uh, you can sort of see discontinuities, right? So from the background, you can identify this person's head here, and then from there, the hairline, certain other edges, right? So you can see these like most of the information about the image can be sort of obtained by these edges, right? Yeah. So so this more compact than pixels. What this actually means is, so if you look at an image, although there's like a lot of number of pixels in the image, right? So imagine there's a image. So imagine this particular picture, right? Here, this entire slide. So there's a large number of pixels, but the number of pixels corresponding to the edge is low, right? So if you look at the entire number of pixels of this particular slide and the edges and then the pixels that corresponding to these edges here are very low, right? The ratio, of course, is very high because uh, the number of pixels is very large compared to the number of pixels here. See, so yeah, and also when you talk about object level knowledge, artists, even an artist when they're trying to draw an image, they start with the edges, right? So these are common sense. And here we are talking about different types of edges, right? So edges also, there are different types. So these edges, so basically if you look at the image, so once you use some sort of like an algorithm, say we are using some algorithm like Canny or something to identify the edges, uh, so it will just identify the edges. If you like give this image to a, if you put this to some edge detection algorithm as an input, it will identify all these edges. But these edges actually mean different things, right? If you look at this, uh, so this I can annotate. So this actually uses surface normal discontinuity, right? So it's like it says, okay, this surface is normal to the background. So it's somewhat like normal to the frame that we are looking at. So it's a surface normal discontinuity, right? And then basically this part is a background discontinuity, right? So it's like it's like separates the image, this particular image out of the background. Then there's a depth discontinuity here. Actually, it's like somewhat like a foreground background change. Once again, we call this background discontinuity as well, right? And then there's the surface color discontinuity. In the same surface, there are two colors, right? So there's a surface color discontinuity. And then there's an illumination discontinuity. So you can see there's a shadow here. So there's illumination discontinuity here. So there's different types of discontinuities actually that you can look at an image and identify, right? So yeah, so here you can see that when you are, so basically just by identifying certain edges without differentiating exactly what these edges are, you can't actually get an understanding of what these features are, right? So that's the whole idea here, just some background knowledge of edges, right? So we'll move further. So I think you all have done image blurring. Separability is like, I think you all did this, right? Like you all use the 3x3 Sobel kernel. You can represent that as a two 1D kernels. I think you all did something like this, right? So for neighborhood operations, I think you might have done such examples where there's two Sobel kernels, somewhat like this, -1, 0, 1, sort of like differentiated by two kernels, right? +1. So it's again -1, 0, 1, something like this. We'll be going through some of these today also. So if you haven't done, so how if there are two certain edges like this, dark, light, what sort of pixel we can use for this sort of thing, right? We can have -1, 0, 1 sort of thing, right? I hope you all have done some similar examples. So this is first, anyway, we'll be talking about this. We'll be mostly looking at the mathematical aspects of edge detection today. So in that case, we'll be looking at how exactly this edge detection works, right? In a somewhat like a mathematical perspective. So in that and how these edges are actually obtained using these kernels. So you all have done, I think, median filtering. Yeah, so these things I think you all have already done. So these are actually not connected with the delivery of this module, right? So these are directly extracted slides from this particular lecturer from, I think, Switzerland. Not exactly sure. Yeah. Yeah. So now we look at edge detection. That's our main concern. So we know what edges are now. So right now we know why edges are important and what edges are actually. So now we'll look at the most important aspect, which is the edge detection part. So if you look at this image, you can see that there's now, we defined edges earlier as a discontinuity, right? We identified edges as a discontinuity in images. So now in this case, you can see there's a discontinuity in this image. There's a white layer, then there's a black background, and then once again, there's another white layer. So now you can see this clearly suggests that there are certain very dynamic discontinuities available in this particular image. Now we are drawing a line like this. We call this line a scan line, right? So in images, when you want to, like, say, analyze an image, we can draw a scan line. It can be vertical, it can be horizontal. So we just draw a scan line like this, right? So this is a scan line. So yeah, so this is simply like, say, imagine this is like a single layer of pixels in this particular, if you look at this, a single layer of pixels, right? So there's one certain amount of pixels drawn in a horizontal way. Now, along these pixels, imagine this particular scan line can actually look at the intensity variation of this image. And if we plot the intensity variation of this image, how do you think it would look like? So I will simply draw the y-axis like this, right? So, okay, I'll draw y-axis like this. So you all know that I'm using the OpenCV format, right? So this axis is X, this axis is Y, okay? So, I mean, you can use any convention, but in my case, I'll be using this. Okay. So you can see this is bright. This is dark. This once again bright, okay? Now, so you can see there's this is actually not a very sharp, so yeah, we'll talk about the place, right? So we'll just for the time being assume that this is a very sharp transition, right? Just forget about this blur over here, right? We'll say this is just white, black and white, right? So if we plot the intensities here like this of this particular image, we plot the intensities of this image like this. How do you think it? So how do you think the intensity is plot? So we'll mark this as I along with Y, right? So you can say intensity of white is quite high, right? Intensity of I is quite high, right? So we can say, okay, this is this part here is bright. Assume that these are very sharp transitions, and then it will go down like this at this particular point. And then once again, you can see right after this transition, there will be a quick spike like this. Assuming these are very sharp transitions. And then it will go on like this, right? So this is the intensity curve, intensity versus y-axis curve. So this corresponds to a bright region. This corresponds to a dark region, right? Low intensity and bright. This, of course, we already know, right? You all have done this in histogram trans analysis on all these things. You all know this already. Now, if we obtain the derivative of this, right? So if we see, now we are looking at, if we obtain the derivative of this along the y-axis, say in this case, if we obtain the derivative, that is di over dy, how do you think the curve would look like? Forget about this image, right? Now we are not looking at about this image. We have obtained the intensity curve out of this image. Now from this image, we are trying to obtain the intensity transformation variation, that is di over dy. So I will draw my intensity variation curve, that is di over dy. So this is the di over dy curve, right? This first derivative, okay? So first derivative. Now we'll say this is the zero line, right? Ideally, it should have been here, but for the time being, I will just put corresponding y1 and y2 terms so that they correspond, okay? Y1 and y2, right? Now, if I obtain the first derivative of this, di over dy, what's di over dy for this part? Di over dy here. Here it's a constant intensity, right? So the derivative of a constant is what? 0. So if you get the differentiation of the constant, it's 0, right? So it's going to be this line, this point. Now, if you come here, you can see there's a very sharp transition from, let's say, this particular intensity value to 0, right? So from positive to negative, there's a positive to negative gradient, right? So, so positive to negative gradient means what? Our There's going to be a sudden spike here downwards in our differentiation as well. Something like this, right? And then once again, it's going to continue. And once again, you can see it's di over dy here. It's 0, right? Di over dy over here, it's 0. And here also, it's 0, why it's constant. And here also it's constant. But here you can see there's once again a sudden transition, see, from dark to bright. So now, if I, so this is once again 0 up to this point. Y2, there's a sudden transition, right? So let's see. Again, it's 0. Now you can see if you get the intensity of an image, and if you get the first derivative of the image and see for these sudden spikes, these correspond to the edges, right? Right. So we can conclude that the edges of an image correspond to the we call this extreme or the extremes of the images intensity functions derivative, right? So that's the whole idea. So if you have, so if you have an image, so if you want to find the edges of an image, what you do is you get the intensity plot of the image, intensity function of the image, and then you get the first derivative of the image, and this extrema of this first derivative will correspond to the edges. Clear? I think that should be clear. That's not very hard to understand, right? Image එකක් තියෙනවා. Image එකේ intensity function එක ගන්නවා. හරි. ඊට function එක ගත්තට පස්සේ මේක ගොඩක් අපි කපමු grayscale image එකට. color image වල පොඩ්ඩක් වෙනස් මේක. එතකොට අපිට එහෙම වුණොත් එම කොහොමද මේකේ partial derivatives වලට යන්න වෙනවා. Right? So in this case also we have to go to partial derivatives that you will understand. So image, of course, here we are looking at one axis and we are looking, because here there's only a vertical edges, right? There's no horizontal edges. So in this case, we can simply go with di over dy, right? Simply go with di over dy. You will understand what this entire thing is. But say di over dy can be used since there's only vertical edges. But imagine there's vertical and horizontal edges. In that case, of course, we'll have to go with di over dy and also di over dx, right? So we'll have to get actually not di over dy, but dy over y. That's partial derivatives of the image in both the axes, right? Separately, right? So that we'll look into, and we'll look into how to get this particular continuous. Now you can see this is a differentiation is a continuous thing, right? Differentiation of a function is a continuous. It's a continuous type of operation. So but images are digital images, right? Images are digital functions, discrete functions. So we can't use basically differentiation, which is a continuous operation, continuous time operation on a digital image or this discrete function. So what we do is we actually have to use these numerical approximations, so some discretized method to do that in a digital image. So that we'll look at that in the next slide. So up to this point, is it clear how the edges are identified? How the edges are identified? Is it clear? I hope so. So if you have any questions, you can ask, right? Up to this point, it's not very hard. So the primary objective, mainly that your focus should on this particular topic, feature extraction, will be on edges, but also we'll look at corners also a little bit, right? So try to get the edges idea into your head properly, right? Okay. So that is clear. Yeah. Okay, right. So now we'll go on to okay. So I couldn't so I'm going to clear the annotations. Okay, if you want, I can give you annotated note later. So yeah, so I will clear these. And so now this actually is the realistic one. Now I told you all to assume here that that these are very sharp edges, right? But in reality, you can see these are not very sharp transitions, right? See, there's actually a blurring happening, right? There's actually blurring happening. So these are not very sharp transitions. So so in realistically, there's this sort of uh, gray level. I mean, what? So it's like some what do you call it? Like some non-ideal transition, right? So so if you draw the plot here, it'll look somewhat like this. See? It'll look somewhat like this. So same thing that I sketched, but so in this part, intensity transformation is not exactly linear. It's somewhat uh, you know goes from positive to negative somehow, but it's somewhat like this, right? It doesn't go to zero to positive. It goes up, right? This is what happens. And once you get the differentiation of this, it will not be uh, a very sharp, it's not like an impulse function, but rather like a curve, right? So anyway, regardless of that, if you get the first derivative of this function, these will correspond to edges, right? Okay. Now, as I said, we have to look at the uh, discretization of this. So yeah. So as I said, uh, this actually edges correspond to the extrema of derivative, right? I hope this is clear. Now we'll go to the next part. Yeah. So yeah. So now basically the whole idea, the definition of the derivation is like uh, as I said earlier. Now earlier we just had only one vertical line, right? One vertical edge here. See, one. So I mean, all the edges are vertical. But imagine an image where you have vertical and horizontal edges both, right? So imagine an image like this, right? Say you have image, uh, you have a box like this, right? In this case, you have vertical edges and you have horizontal edges. Now, in this case, if you just draw your scan line like this, you will only catch the uh, vertical edges. You will just go through horizontal edges because this is dot product, right? Dot product. So you just go through the horizontal edges without any uh, notification, right? So, so in that case, what you have to do is you have to once again look at the image at image gradient in the horizontal along y-axis and at the same time along x-axis as well, right? So then only you will be able to understand that the uh, image has horizontal and vertical edges, right? Okay, so I think that is clear. So now we'll go to the next slide, and we'll see here. Now, here what we're trying to do is we are trying to get the partial derivative of this image uh, with respect to x initially, and respect to I think I'm sketching here on the slides, I guess. Wait. So yeah. So now you can see here So we are actually getting the corresponding images. We are getting the derivative with respect to x, right? X here. So now, so we are adding a small, small, what do you call this, increment with respect to x, right? So, but I think I just wanted to check out whether I'm annotating on the slides so that I can just directly share the slides with you, right? So what we're doing is we are, uh, by definition, we're trying to get the uh, partial derivative with respect to x, right? So idea is we have this small increment. Divide by the small increment, add the small increment to x, keep y as a constant, and then send the x limit to 0, right? So this is the basic definition of a partial derivation, right? So if you are no differentiation by first principles, right? What do you call this? Prathama mode dharma vashena avakalanya. If you probably might have done for your A levels, right? Uh, so uh, So similarly, partial derivation is same thing. You add a small increment, you divide by the small increment, and send the small increment to 0, and you get this, and you sort of subtract f minus xy, okay, of this. But this small increment. How can you define a small increment in a digital image? You can't, right? Because we have pixels. Um, because you can't have this continuous. Now this is continuous. Uh, this is continuous, right? Continuous time function, and will not work for images, right? Since it's discrete, right? So in that case, what we do is we have discretization. We have discretized this, right? And after discretization, you will get instead of the small increment, we will have 1, right? So this 1 will actually be 1 pixel, right? For an image. This will be 1 pixel, right? So basically what we are doing is the whole idea is like, it's like this. So if I will try to say an example, right? So imagine we have an image like this. We have an image like this. We have image y, image x, and so this is the x and y of the image, right? Axis of the image, and we'll take one for 1 pixel, that is x and y of that image, and then so this particular pixel will be here, right? This pixel will actually correspond to this, right? XY. This is fxy, right? This image is f, right? Imagine fxy image is this, right? And then this image will correspond to this. What we are doing is, so x plus 1 is what? X plus 1 is this. So can't I change the color of this? Sure, color, yeah, I can. No? So if I x plus 1 is this, right? X plus 1 because x is in distinction. X plus 1 is this. So keeping the y-axis constant, I am getting the difference between this. Yeah, I'm actually subtracting this pixel value by this. මේකේ pixel value එකෙන් මේකේ pixel value එකෙන් මේක අඩු කරලා බලන්න ලොකු difference එකක් තියෙනවද කියලා. Same thing as finding the differentiation, right? It's like you call this so we can call this as the approximate partial derivative in x direction. Next direction, right? Okay. So any question up now? So you can basically do this operation for each of the pixels, right? And you can find out if there's a significant. You can get the. You can basically get, if you plot this. If you get the result of this, if there are images, so wherever there are edges, there will be a sharp difference, right? When you get this thing difference like this. So I hope this is clear. Any questions up to this point? This is not the way that we do it. So we'll see so now okay. So we have this idea. So what we did was we had this idea. We had the idea of how to find the edges. So basically, if you look at what we have done up to now, we had the idea of how we can actually get the edges. That is basically by looking at the image and find out if there are any rapid changes in the image intensity. So how do we find the image intensity rapid changes? By getting the differentiation of the intensity function. So when there's once you get the differentiation of the intensity function, you can figure out if there are rapid changes in the rate of change of the intensity or rate of intensity variation. There, of course, there will be this extrema of the function. These will correspond to the edges, right? So this was actually, now in this case, we did we had the scan line in the horizontal direction, and we by having this scan line in the horizontal direction, we found out in vertical edges. Now what we did was we defined a generalized function for x and y directions in continuous time to figure out how this will vary in mathematically. So we actually got this mathematically a generalized expression. If you want to do this for y, what will do? What will you do? You will have x. For y, the function will be what? For y, the function will be dabba f xy, that's the image, dabba y equals sigma. Sorry, I think it's not sigma, it's epsilon if x plus. I will take a separate slide and write this, right? I will take a separate slide and write this. Okay, I think I'll have to. I'll just leave it for the time being. And I will write I will write the same thing for y, right? So function for y direction. Guys, so the meeting will end in like 1 minute's time. So you can join the link once again, okay? Same link that I shared. I will end this meeting now and we'll continue in like another, after we join.